Okay, so in this lesson I'm going to go over home heating and cooling systems and some of the basic aspects of each of a whole bunch of different systems, and also the basics of how combustion works. So heating and cooling buildings. This is one of the primary things that we deal with as energy auditors is the heating and cooling buildings, right? So we looked at some of the ways that buildings use energy. Water heating is one, lighting, and electrical appliances and other base loads are part of it. But heating and cooling are two of the major components of the energy use in a building. So we want to think about what really makes buildings too hot and too cold. And it's mostly because of heat movement. This is really important. It's mostly because of heat movement. So when a building's too warm, this is intuitive, it's because there's too much heat, right? So let's say it's a hot summer day and there's heat coming in through the walls, and through the windows and so forth, right? But also contributing to that is heat that's added to the building through things inside the building, right? People and electronic equipment, lights, and cooking, the cooking facilities, whatever. So there's all kinds of things that are adding heat to a building that make it warm. Now, in the heating season, like what makes a building colder, it's primarily because we're losing heat to the outside air. It's primarily because we're losing heat to the outside air. So it's about heat movement. Or temperature control is primarily about heat movement. Now there are some, if the air is cold outside and it's leaking inside, there is some cold air that's leaking in. So it's not just about heat movement per se, it's also about cold air moving in, but it's primarily about heating. Right? So cooling season, it's the heat that's coming into the building, we want to get rid of it. In the heating season, the heat is leaving the building. For the most part, that's the problem. And we want to basically get heat back in the building. And we can do that with any number of means, and we'll go over a bunch of them. Okay? So either way, we're kind of dealing with heat movement. That's our primary battle, so to speak, keeping a building warm or cool. So combustion, the real basic combustion reaction is you take a fuel, you need enough oxygen, and you have enough heat, and then there's using some other impurities in there. And then the result is you have your, again, this is a fuel source. This is assuming it's some kind of a hydrocarbon like wood or oil or natural gas. They're made mostly of carbon and hydrogen. Okay, and so when you take carbon and hydrogen, right, and you add oxygen to each of them, you end up with carbon dioxide. This is water vapor, right? And then you generate heat, of course, so that's like the heat emanating off this fire. And then any other impurities, leftover carbon, nitrous oxide, sulfur dioxide, whatever. So there's other impurities. But that's your basic combustion reaction. And what this is sometimes, the combustion components are sometimes referred to as the three-legged stool. So if you think about a stool that has three legs, if one of those legs is missing, the stool is going to topple over. And that's the same thing with combustion. If you don't have enough oxygen, right, so if you starve a fire of oxygen, you could have all the fuel, all the heat you want, it's not going to burn, right? Same thing if you have enough oxygen and you have enough heat, but you run out of your fuel source, right? So the wood burns up, there's no more fuel, fire's going to go out. So you need all three of these in the right amounts in order to continue the combustion reaction. And this reaction, what are the nice things about it is it's exothermic, so it's taking this chemical energy from inside the fuel source, so whether it's wood like here or natural gas you're burning in a furnace, whatever, and it's converting the chemical energy into heat energy, and then this heat energy is used to continue to feed that combustion reaction. So when you start a fire like here, that heat that's released from the conversion of the chemical energy in the wood, okay, to thermal and radiant energy, that heat is then used to feed the combustion reaction and keep it going. As long as there's enough fuel and as long as there's enough oxygen, it's going to keep going. Okay, so that's your basic combustion reaction. We'll get back to this later in the semester and look at sort of incomplete combustion and some of the dangers of carbon monoxide and so forth. That's basic three-legged stool of combustion. Okay, so we're going to go over all these different heating and cooling systems, and we'll sort of think about when we go over each of these on the left. Okay, so all these here on the left, we go over all of these, and we're going to think about all these questions for each of these. How does it generate heat or cold? How does it distribute heat or cold? And sort of like describe the heat transfer. Okay. Okay, so first, some real basic stuff about how a heating and cooling system works. You probably know this, but just in case, we'll think about how does a thermostat work. Okay, so a thermostat, in this case, the thermostat is actually here. This is a smart thermostat. It has a set point. It has a temperature sensor, and if the temperature drops below that set point, it'll tell the heating system to put the heat on until it goes above the set point. If it's cooling season, if it's in cooling mode, and it goes above that temperature, that's right here, right? So there's just a sensor. You need to know where the sensors are, and that's actually a really important consideration for a thermostat installation. So it's just sensing the temperature of the air around it. And when in the cooling season, if it goes above the set point, it says, hey, to the air conditioner, to the central air unit, we need to cool the air down. It cools the air down until the temperature drops below the set point. Now, excuse me, there's something called a deadband in there, so it doesn't. There's a couple of degrees where it's not going to like shut off automatically when it drops just below, because otherwise it would keep turning off and on too much. That's basically how it works. Now, the modern residential sensors or thermostats actually can have some external sensors. Like this thermostat here is a smart thermostat, and you can usually hook up these wireless sensors to it and put the sensors in other parts of the building, and it'll sense the temperature there, and it'll manage the heating and cooling based on that. But generally speaking, it's right here in that thermostat on the wall. Okay, so you want to consider where to put the thermostat. That's actually a really important consideration. And this can pop up in energy auditing. So if someone has a thermostat, you can see over here on this diagram, maybe it's hard for you to see, but you don't want it on an exterior wall, right? So there's a window here. That wall is probably colder than the other walls. So you think about what's happening, it might think like it's cold in that room all the time, when really it's just that wall is colder than some of these other areas, and then you end up adding too much heat to and there'll be, the other parts of the building will probably be too warm. You don't want to put it next to an exterior door, the same reasons, right? So it can get too cold or too warm. Let's say this is next to a door and it's a hot summer day. Someone just leaves the door open a crack. It's really hot right just around the thermostat, and it just says keeps calling for cold, cooling and cooling and cooling and cooling. It cools down the rest of the house too much. That can be a problem. So you really want it about 3 to 4 feet on an interior wall. That's really, you don't want it like sitting in somewhere where it's coming in direct sunlight from a window, because again, that'll heat it up, right? You don't want it on an exterior wall. You don't want it next to the door. This one, you don't want it next to, this is a radiator, so you don't want it next to like something blowing warm or cold air on it, because that'll just mess the whole thing up. Okay, so that is important. And this may pop up when you're on an energy audit, so you want to look at thermostat pricing. Generally speaking, most of the time these are installed properly, but it is worth considering. Okay, so we'll start with the forced air system. This is something we'll see a lot of in modern buildings. We're not going to go over all the components today, but I want you to get the basic principles. So a forced air system is exactly what it sounds like. It forces air across into ducts, like it basically forces air out into the building. Okay, and there's a couple terms you should jot down. You should know what a supply duct is. So the supply duct supplies the air to the spaces, and that would be that's located up here. right? So the air handler is what actually forces the air itself. So in most of the systems, you're going to see an air handler looks a lot like this in the little cabinet at the bottom of the unit. And this has a blower, and this air is just blowing out. There's just a pretty powerful fan that blows the air out this way. The return duct brings the air back into the air handler, back into the forced air system. And so you'll see a theme here as we go through most of these. Basically, everything operates on a loop, on a circle. And the forced air system, what it does is the blower blows air across either a warm or cold coils or burners, heat exchangers. So it could be hot metal or cold metal, basically. So it blows air across the metal, forces air out the ducts into the house, okay? And then that air from that goes out into the rooms, and there's an example of it here, right? So it goes out, okay? It goes out to supply registers, supply ducts, and then it comes back the return. So there's different setups for returns. Usually you want a return vent in every room. You can have a whole floor return, sometimes a whole house return. But the point is, this air is blown out, and then it actually, what the air handler does is it blows air out, and while it's blowing air out, it's actually pulling air back into the return, and it's just circulating through, right? So it's basically blowing it out, pulling it in, heating up or cooling it down, blowing it back out, pulling it in, so it's all a circle. Okay, so all basically a loop. So that's your forced air system. And the forced air is a type of system. You can have forced air with like a gas furnace. You can have forced air with electric resistance. You can have forced air with a heat pump. So there's forced air is sort of covers a couple of different systems, right? So here's just a sort of a diagram of forced air system. Gives you a good sense. Like here's your supply duct that's going out. Okay. In this case, we have actually two different systems. So this is the supply to the first floor. Okay. And this is the return that's going back. You can see there's multiple returns going back to that. This one also has an air handler in the crawl space. Right, so a couple of supply ducts, and then there's one whole floor return that goes up in the middle. And that's not uncommon, but there's different ways. These are both forced air systems. They're just two different systems. Okay, so then we have forced air natural gas, which is a forced air system, obviously. And this is just for heating, and it uses natural gas to heat the building. Pretty simple, really, conceptually anyway. Big metal heat exchanger. Okay, so this is a thing. It's probably, I don't know, a couple feet tall and like a foot wide or so. And you can sort of see in here there's like a tube. Okay, so what happens is you have burners that natural gas burners that they burn the natural gas, which heats up the air, and then the air just gets buoyant. Okay, so and it goes up through these heat exchangers. And then this heat exchangers in here, in this cabinet in here, okay, and the blower, okay, the blower just blows the air across this hot metal, and that's it, right? So it blows air across the hot metal, the air picks up the heat, and then blows out the supply ducts. And that's really it. And so the heat transfer here is you have the chemical energy in the gas, which is then converted to thermal and radiant energy when it burns, and then it's actually taken as convective. It's conductive, conducts into the air around it, and then it's convective energy that goes up and travels with the air, and then the air comes back and heats up, and it's a loop. So that's your forced air natural gas. Electric baseboard, entirely different way to heat a room. So you may have seen something like this before. There are also some hydronic baseboard, but electric baseboard is just electricity. This just gets hot, so has a high resistance, and it's these wires inside of here. It's like a space heater, right? So that's an electric Same principle, just the metal gets really hot. So it gets hot, but the way this actually heats a room is you get what's called a convective loop. So you want to jot down the convective loop. So what a convective loop is you get this warm air here that rises right through convection, and it hits the ceiling and it can't go any higher, so it's forced to go because it's moving, right? And so it actually creates this heat current of heat, okay? Warm air, basically. And it actually sort of goes across, and then as it cools down a little bit, it sinks. And at the same time, because the air is moving up here, okay, so it's moving up from the baseboard heater, it actually creates a little mini low pressure zone. When you move air away from somewhere, it creates a low pressure zone. And so this air is actually pulled toward, because it's higher pressure, and so it's actually pulled toward the baseboard heater. What you end up with is this current. Now you can't really feel it, but what happens is over time it sort of slowly heats up the room. Not the most comfortable type of heat always. It can get a little cold down by the floor, but once these convective loops start going, it takes a little while to heat up, but once you get it going, it actually tends to be fairly comfortable. Whereas with the natural gas forced air, it's like pretty quick. The house will heat up. It doesn't take quite as long. But the principle here is it's a convective loop, and you'll have like baseboard heaters in every room, and you create a different convective loop in each room. Okay. Oh, and in this, the heat transfer is electricity that's converted directly to thermal energy, and then radiant energy. So then we have oil hydronic, which will use a baseboard as well. Okay, so this is an actual picture of the inside of one of the baseboard hydronic systems. And so this actually sends hot water through loops. And then there's these little fins inside of these metal loops. And when the hot water hits the fins, they like protrude into the inside. Let me draw a little. Like if you have these fins here. So here's your tube, right? And they have these fins like this. You can sort of see them over there. And these fins like protrude inside. I don't know exactly what they look like. Basically the hot water flows through here, hits this, and these whole fins heat up, and then that'll create your convective loop. And that's what this is. The water is going to be flowing through here like this. And what you have is you have an oil boiler that burns oil, makes the hot water, or dumps the heat into the water. Okay, and then in this case, it has to have a pump, right? So there's be a little pump here, which is not pictured on here. But anyway, there's going to be a pump down here, and that's going to pump the water through here. Okay, and then it's going to go through. In this case, you have multiple loops. And you end up here with a convective loop where each of these are. So these are your baseboards, which are pictured here. And then it just loops back again. Everything's a circle. So you have the water that goes out, dumps some heat out into the building, and then comes back, cools down, comes back. It's heated back up by the boiler. So these usually, there's different styles of this. There's on demand, or there's some that are thermostatically controlled where there's a tank in there that just keeps the water at a certain temperature. That's your hydronic, oil hydronic. That's a picture of a old, very old oil hydronic, right? So here's your hot water supply, so that goes out to the baseboards, and this is the return that comes back, and here's your tank. Here's your burner. Yep. And then here's the, where the gases go. So this is a combustion appliance. Okay, then we have central air. So the important thing about central air, so the central air uses that vapor compression refrigeration cycle that we talked about earlier, right? So if you think about, so central air is cooling only. Central air is cooling only. Now, these will have your outdoor unit and your indoor unit. Okay? And then you have your refrigerant lines. If you remember your vapor compression refrigeration cycle, you're going to have two refrigerant lines, one going in and one going out. Okay? And that's the vapor compression refrigeration cycle, right? And so outside and inside you have coils. So if you think about, if we're cooling the building, I want you to think about, if we're cooling the building, where would the evaporator be? Remember what the evaporator coils do. So the evaporator is going to be inside. Because remember, to evaporate, you pull heat. You need to add heat to the refrigerant to evaporate it. Okay, so with our central air system here, inside we'll have an evaporator, so there's coils inside, and what happens is, so here's your refrigerant line. There's going to be one, usually they're both insulated, but one, their cold line is going to be insulated to prevent condensation and heat loss. So you have evaporator inside, and what's happening is it's pulling heat in here when it evaporates, and then you have, remember, you have a cool gas that's going to come out here. Okay, you have a cool gas coming outside, and then here's your compressor and condenser are both in the same unit out here. So then you have you dump the heat out. So this fan is used to blow air across these coils. Okay, so it just pulls air across these coils, and you can actually see the coils in here. So here's some coils, and here's some coils. So the refrigerant goes through there, and the fan pulls air across it, which facilitates the condensation process, dumps the heat out, goes back in here, evaporates, pulls heat, takes it, dumps it out, and so on. Okay, so that's how a central air system works. Okay, and this is a forced air system, so you can see here's your air handler, here's your supply ducts, here's your return ducts. So this will just have your coils inside that blows air across those cold coils, and that's really it. Okay, so there's two separate loops here. You have your sort of refrigeration loop from inside to outside, and then you have your the air loop on the inside. So central air is cooling only. Okay, and this is often referred to, anything that looks like this, so a heat pump or central air, is referred to as a split system. Split meaning you have an outside unit and an inside unit. Outside unit, inside unit. So it's split between inside and outside. Okay? So then we have heat pump, which is the exact same thing. Uses the refrigeration cycle, but in this case, the evaporator, so a heat pump can cool or provide cool air or warm air. Okay, so cold air or warm air. So with a heat pump, the evaporator and condenser switch roles. So if I am in cooling mode, okay, if I'm in cooling mode, then my evaporator is inside, because I need to, again, I need to pull heat from inside and dump it outside. If I'm in heating mode, it actually flips, and my evaporator is outside, and my condenser is inside. So if I'm in heating mode, I take heat because I'm evaporating outside, and I dump the heat inside, and that's what I blow out into my supply ducts. Okay, and we'll go over that in a little more detail at a later time. But that's really important to remember. Central air is cooling only, and then a heat pump is heating or cooling. Okay, and the split system, again, is when you have an indoor and an outdoor unit. So that's our heat pump. Oh, and by the way, with the heat pump, because it's the refrigeration cycle, you're not converting electricity into heat. you're using electricity to drive the compressor. Okay, so remember the compressor is what uses most of the energy, and that's what causes the latent heat transfer. So you're not actually, the reason this is important is because if you put in 1 kilowatt hour of electricity into a heat pump in heating mode, you're actually normally going to get more BTUs of heating than is in the electricity. And that's because you're not converting electricity to heat. You're using the heat to drive the refrigeration cycle. So I'll post this video. I don't want to. It's a really good explanation of how a heat pump works. So make sure you watch that. So an air source heat pump is a heat pump that uses the outside air as its heating source or its heating sink. Okay, so an air source heat pump uses the outside air. So this is easy to think about in cooling mode, because you're just taking heat from inside and dumping it outside. It kind of makes sense, right? Like you have a warm house, you have this evaporator inside, and you cool it down, and you take the heat from inside the house, you dump it outside. Right, so that would be here. So this is heating mode, or cooling mode, excuse me. So you have the evaporator inside, and it dumps the heat outside. Okay, so this is the heat going out. With an air source heat pump, what's really interesting is that when you heat the building, okay, when you heat your building, right, so here we're in heating mode. When you heat the building, you're taking heat from outside and dumping it inside, which again may not seem like that odd, but think about it. There's times where you're using a heat pump. It could be 30 degrees outside, so the new heat pumps, you can be 20 degrees, 25 degrees outside. And think of that, you have 25 degree Fahrenheit air outside, and you can still pull heat from there and dump it inside. So that's an air source heat pump. Air is the heating source and the heating sink. So the colder the air is outside, the more difficult it is to pull heat from it, and the less efficient your heat pump operates. So a heat pump will operate at its maximum efficiency when it's like a nice cool fall day, 60, 50, 55 degrees outside, 60 degrees, whatever. As you drop the temperature, it has to work harder to provide the same amount of heat. And the same goes here. So on a nice 75 degree day, it's not too hard to dump heat in there. But if it's like 100 degrees outside, it's hard for this system to keep up, because it's just you can't dump as much heat in there because the difference in temperature is not as big. So heat pumps operate most efficiently at these sort of moderate temperatures. The hotter it gets, the less efficient it is at cooling, and the colder it gets, the less efficient it is at heating. But that's your air source heat pump. There's also some of these hybrid systems, this is a really common one, a natural gas hybrid system with a heat pump. So this one can use both. Okay, so you can use the refrigeration cycle to heat and cool, so it operates as like a regular heat pump. But then if it drops below a certain temperature, and this depends on the system and the type of system and the efficiency and the quality and so forth, if it drops below a certain temperature, it just may not be able to keep up and keep the house warm enough. Or in my case, so I have a hybrid system, and I've set it so that I know how efficient it is, and as the temperature drops, the efficiency drops, and it becomes, at a certain point, it becomes cheaper to use gas than it does to use the heat pump, and that's where I have my system set to change to the natural gas. But anyway, it's usually in a climate where it can get really cold sometimes, but it's generally not that cold, and so you don't need the gas heat all the time, but it'll do it whenever it gets particularly cold. And other than that, it's the same. It's a forced air system. And what's really nice about this is that you just have one unit down here, and you'll have gas burners, and you'll have coils in there, and you can use whichever one. Okay. Right. So here's an example of a hybrid system. Yep. So you can see the refrigerant. This is your split system. Your refrigerant line coming in, and then it's kind of hard to see, but these are this is a flue with natural gas. And so you can, it's just one cabinet, one duct. Here's your supply duct, here's your return duct, and you can use both in the same. So it doesn't use a lot of extra equipment. Okay, just a couple more. We have a ductless mini-split. These are becoming much more common. Okay, so these are ductless, as the name implies, and these use the refrigeration cycle to heat and cool. Okay, so they can heat and cool, so they're heat pumps. So what you have, this is a split type of system, and you have an outside unit, and then what you have is you have coils outside, and then you have coils in these terminal units inside. But instead of having, like, there's no ducts involved here. So what this does is it takes these refrigerant lines and goes right to the heat and cooling distribution. So these refrigerant lines will connect right up to this box, and then this will either release heat or pull in heat. So it would be either an evaporator or condenser, depending on whether you're heating or cooling. And so here there's a little fan that blows out the warm or cold air. And what's nice about this, number one, super efficient. These are the most efficient heat pumps out there. Number two, you can zone these out much more easily than with a ducted system or a forced air system, because you can just have these terminal units, and you can have multiple terminal units for a single outdoor unit. And so if I have 4 rooms down here, I can put one unit in each room, and I can control the temperature in one room and make it a different temperature than another room. So they're much easier to zone out, whereas with ductwork, it's much more complicated. And so these are becoming really popular because prices come down, because they are really efficient, because you can zone them out. It's also really good to retrofit older buildings that don't have ductwork in the walls already. So like historic buildings in particular. You go to Europe, for example, and these old, hundreds of years old buildings, and you'll see a lot of mini splits there, because you don't have to add ductwork to them. You can just add pipes. Okay, they're like little copper tubes. So that's your ductless mini split, becoming more popular in the residential setting. Then we have just general window unit. So a window unit uses the refrigeration cycle. Okay. So with a window unit, this is an AC unit, so this is cooling only, and you have coils inside. Okay, so you have some coils inside. You have coils outside. Here's your compressor. So you have your condenser outside, right? Remember, your evaporator's inside. Evaporator pulls in the heat, dumps the heat out the back. Okay. So if you put your hand on the back, the outside part of a window unit, it'll be warm. It's because it's dumping that heat out there. This one they'll have like a little blower that'll blow air across these evaporator coils, and that's where you feel that cold air coming out of a window unit. That's what you're feeling. And there's different styles of this. They make these ones. This is probably the one you've seen more often than not. But they make these ones that are kind of larger. They're generally not recommended to use them because they're not as efficient as central air, but if in a pinch, you can use them. But again, it's just the refrigeration cycle. Okay, then we have steam radiators. So we just have 2 more. So steam radiator is exactly what it sounds like. It uses steam. Okay, so you'll see these only in older buildings. What you have is a boiler usually down in a basement, generates the steam. The steam goes up the pipe. And what happens is when the steam comes through here, it hits the metal, and remember it's steam, so it's vapor, right? So it hits the metal and actually condenses into a liquid, and then these get hot and release that heat out. They're radiators, and they radiate heat out. And there's different styles of this. Some of them will be like you'll just have a continuous loop that'll go through here. But the older ones, you'll have a lot of times a gravity-fed system where you'll have steam coming up and then you'll have liquid water just draining back down. But either way, the water has to drain down. Okay. And so in this case, steam, so vaporized water, is what's carrying your heat, and that heat comes from a combustion, usually oil, but sometimes gas. The old ones were coal. But either way, you take the chemical energy, convert it into thermal energy in water and latent heat and vapor, and then you release that out as radiant energy. And again, it's a loop. The water comes back, drains back down to the tank, heats up, boils again, and so on. Okay. So that's a one-pipe system, which just means it drains back the same pipe. And the last but not least, we have in-floor heating. Not as common, but a very, very comfortable style of heat if you can do it. Okay, and so this usually it's going to be pipes like hot water. So a lot of times these are hydronic systems, and you have hot water in these pipes that are running through the floorboards, and then it just makes the floor warm. The floor radiates up. And what's really great about radiant, look at this diagram down here on the left. So if you have your forced air, you have this like currents of air, and it's like warm here, it's really hot here, and it's kind of cold over here. With radiant in-floor heating, it's just a really nice, even warmth. Your feet are warm. It's warm all the way through, and then the coolest part is up high, and where people normally aren't. So, and you can even add like a fan up here and kind of keep that circulation going. But radiant heating is a really comfortable way. A lot of times it's hydronic, but you can also do it with electric resistance too. So there's in-floor heating with electric coils, which is not as cost-effective usually, but it's still really, really comfortable. And it primarily heats through convection. Okay, so I know that's a lot, but we are going to see a lot. Well, we'll see. I don't know what systems we're going to see this semester. I'll try to expose you to as many of these systems as we can, but I wanted to give you a foundation of all these different heating and cooling systems. And hopefully as we go throughout the semester, we'll see examples of each of these, or at least some of them. And you know, the more times you see these, the more you'll recognize them. But I've encountered all of these except for steam systems in residential buildings, but it's good to have this foundation. Okay, and that's it for this presentation.